Good afternoon. My name is Daniel, and this is the presentation on the production of ultra-cold neutrons at the Los Alamos National Laboratory. Behind the words is an image of the particle accelerator that is used at the laboratory to produce these neutrons. We'll get into the details shortly. Ultra-cold neutrons are free neutrons that could be created and stored in order to be used for later experiments. They have very low kinetic energy and have favorable properties for various experiments. The equation on the top left there is the Fermi potential of the ultra-cold neutrons, with m being the neutron mass, capital N being the number density of the neutrons, and lowercase a being the neutron scattering length in terms of femtometers. We also have a little diagram of a neutron down below there. Now, the benefits of ultra-cold neutron production have been well studied for the past couple decades. Ultra-cold neutrons are very efficient in experiments involving radioactive decay, neutron lifetime experiments, neutron magnetic moment, magnetic dipole experiments, neutron-based sensors and imaging. Various fields require ultra-cold neutrons based on their stability and their long lifespans. And this project is about creating ultra-cold neutrons where they can be used in other experiments. Now, the way we are going to create these is through a machine and through spallation. Now, spallation is where we will bombard a target made of tungsten alloy with protons, and neutrons will shoot off of this target as a result. And because of this solid deuterium, an ultra cold compound is going to be used to lower the energy of these neutrons that are produced through spallation. And thus, by lowering the energy of these neutrons by cooling the temperature of the entire vessel, in the diagram here, we are able to produce ultra-cold neutrons, which can then be captured and stored for later experiments. Now, various projects have been done at PSI as well as Los Alamos Neutron Science Center. These are both national labs, and they produce ultra-cold neutrons for various experiments and have studied that solid deuterium is a reliable source for this ultra-cold neutron production. Now, the goals with our experiment would be to test the efficiency of this system and produce ultra-cold neutrons on a run from about 2 to 5 hours, maybe between 3.5 and 5 hours. So producing ultra-cold neutrons for this amount of time should get us on the order of 10 to the 7th or 10 to the 9th ultra-cold neutrons, which can then be used for various experiments in the future, as mentioned before. Now, behind this image is a image of the Los Alamos Neutron Science Center. Now, we can see in the for about just an inch to the right of the center is a long row of buildings. That's the particle accelerator, and the various buildings scattered around are various laboratories where a lot of good work is being done to this day. So we'll go through an equipment list for this project. The first thing we would like to provide is a tungsten alloy target. Now, this target is going to be bombarded with protons in order to produce the neutrons that will in turn be cooled into ultra-cold neutrons. a proton beam is required, and at Los Alamos, we have the opportunity to utilize a high energy 800 mega eV accelerator to bombard our tungsten alloy with protons. The vessel that will house the solid deuterium is described here. There is a component made of beryllium. It is a reflector that encases the solid deuterium volume in a cylinder. And the tungsten target is at the bottom of the cylinder. So when the neutrons get created and they start coming up the ladder, the SD2 will work to convert the neutrons that have been created through spallation into ultra-cold neutrons by lowering their kinetic energy through phonon interactions. Now, the energy in the neutrons through these interactions with the solid lattice of the solid deuterium are able to change their energy by creating additional phonons, which are vibration particles. Now, through vibration and through lowering the temperature, these neutrons are able to become classified as ultra cold neutrons, and they then get transferred out of the vessel and to the containment area to be used for later times. Continuing on the equipment list, we have a polyethylene layer in between the solid deuterium and the beryllium reflector. Now, this layer helps to cool the neutrons, and it helps to produce the ultra-cold neutrons by keeping the environment ultra-cold. And by ultra-cold, it's around 10 Kelvin, between 5 and 15 Kelvin in this environment where they are producing these ultra-cold neutrons. Additionally, we will need to have temperature sensors to monitor the activity inside the vessel, and temperature control systems in order to adjust the temperature in the vessel depending on how efficient we want our ultra-cold neutron production to be. Finally, the last parts of the equipment list would be biological shielding for safety. The entire assembly will be housed in over 2 meters of steel and 1.8 meters of concrete. Now, this helps to keep any radioactive material away from humans, away from our operators. And additionally, the vertical guide that takes these ultra cold neutrons that are created and brings them to the storage area is stainless steel, but it's also coated with nickel on the inside. And the nickel allows the neutrons to flow freely to the containment area. There's a butterfly valve in the cylinder that allows the neutrons that are created to escape into the steel tube and be transported. And it opens on a frequency of about 0.1 seconds to allow particles to escape. Finally, an ultra-cold neutron detector at the end of the transport system allows the neutrons to be counted and analyzed as they are being created. And this is through an experiment which Los Alamos calls the time of flight experiment. Judging from the data, it pretty much describes the time it takes for an ultra-cold neutron to be created, to move through the transport system to the detector. And obviously, these are very short amounts of time, but we can gather large amounts of data through these instruments here. Here's a graphic of the ultra-cold neutron production. We can see the different components here. On the lower right here, we see liquid deuterium and heavy water used as the source. In our production, we're going to use solid deuterium as the source. This solid deuterium source has been proven to be more efficient in the production of ultra-cold neutrons. However, the cryostat where the neutrons are created and the general assembly of this system is pretty similar to what we would have in our proposed experiment. And on the lower left there, you could see that the ultra-cold neutrons are being transferred to the experiment area away from the system. So moving on to the estimated cost of this project, an accelerator costs a lot of money to rent, between $3,000 to $10,000 per hour. If we are to do this experiment at Los Alamos, we would be funded by the U.S. Department of Energy, and we would not need to rent their accelerator. The same is true about the cryostat and the housing and the rest of the system that they have. We would just need to rent the facility for our experiment. That will come on the next slide. We have our tungsten target cost broken down here. And in the background there, you could see one of the production facilities for ultra-cold neutrons. Moving on, we have the description of the cryostat. Now, to purchase these is upwards of $100,000. Now, this includes the lab-grade materials. Aluminum and nickel would be coated on the inside of the cryostat in order to allow the ultra-cold neutrons to be produced and to leave the cryostat freely. This would likely be, like I mentioned, over 100,000. Luckily, we can use the Los Alamos facility for a price. We would provide the sensors for our experiment. They're about $400 each. And we would also provide the solid deuterium on our own, which would be about $400 per liter. So we estimate about 2 liters would be needed for our 5-hour run. Finally, we have staff costs. I would suspect a team of about 5 researchers to be paid $50 an hour can get this project done in about 1 to 2 work days. A 3 to 5 hour production run with a little bit of extra costs would be most likely just a little bit under $4,000. Now, renting the ultra-cold neutron production facility at Los Alamos for about 4 to 7 hours while we perform our experiment and gather data would cost between $2,000 to $3,000 per day. And just to be safe, I would suspect there'd be at least 2 days of work. 1 day of preparation and 1 day of ultra-cold neutron production and analysis. Any extra cost for maintenance, we added in an extra 15% of our cost. So for our total cost for our 3 to 5 hour experiment, producing ultra-cold neutrons would be just under $19,000. $18,666. And that is a rough estimate, mostly on the conservative side, considering maintenance and staff. Our project wants to achieve these goals, and we want to produce ultra-cold neutrons. And if we were to work like this on a regular basis for the course of a year, we would expect to run this 3 to 5 hour production experiment once a week. Now, there are 52 weeks in a year. I don't believe we would produce these neutrons every week of the year. There must be some weeks for maintenance, some weeks for data gathering, some weeks for analysis, and some weeks for compilation of data and maybe drafting up a report once or twice a year about our progress. So For the entire year, we have a high budget of about $970,000, a little bit over, almost 971. Now, this is a high estimate. I suspect the real amount will be thousands less, as we are only expecting to produce these neutrons and run the experiment for 3/4 of the year, about 39 weeks, and it could be even lower. So 728,000 is a little bit closer to our expected price for this experiment for 1 year. Now, to conclude, we have known that solid deuterium is a reliable source for ultracold neutron production. Utilizing the facilities at Los Alamos, which are funded by the U.S. Department of Energy, government-funded facilities, we don't have to spend out-of-pocket costs for some of their equipment. This lowers our entire cost and allows us to put our budget under $1 million for 1 year of ultracold neutron production. I believe that even in the short-term production of ultracold neutrons, we can supply experimenters with a steady amount of UCNs so that they can complete experiments and make our world a better place. Now, I'm proud to show this to you guys. I hope you enjoyed the information. I really learned a lot. I hope you guys did too. The background of this slide is one more shot of the Los Alamos Neutron Science Center with the desert in the background. What a nice place to work. That's what I would say. Well, I hope you enjoyed our presentation, and I hope you will think about ultracold neutrons every time you imagine a particle accelerator. Thank you for paying attention, and enjoy the rest of the presentations. Thank you.